Hello everyone. Thanks for visiting my channel, Mr. Professor, or as we say in Korea, 교수 아재. Today, we're going to handle a problem connecting two classical theorems, Fermat's little theorem and Wilson's theorem, through polynomial algebra over a finite field. The big picture in one sentence. Over G sub p, the polynomial x to the p minus 1 factors completely as x minus 1 times, x minus 2 times, up to x minus p minus 1. And plugging x is 0 into that identity hands us Wilson's theorem. Let's build that up carefully step by step. The problem has two parts. Part A, for any prime p, prove that over g sub px, x to the p minus 1 is equal to x minus 1 times, x minus 2 times, up to x minus p minus 1. Part B, by comparing constant terms on both sides of A, deduce Wilson's theorem. P minus 1 factorial is congruent, -1 mod p. The proof uses exactly 4 ingredients, and I want to name them now so you can track where each one entered. 1. Fermat's little theorem. If a is not equal to 0 in G sub p, then a to the p minus 1 is equal to 1. 2. Polynomial divisibility. If a is a root of f, then x minus a divides fx. 3. Degree argument. If two monic polynomials have the same degree and one divides the other, they must be equal. 4. Constant term comparison. Substitute x is equal to 0. Tools 1 and 2 get us roots and factors. Tool 3 closes the factorization. Tool 4 produce the factorial. Keep this roadmap in mind. Set hx is equal to x to the p minus 1 in G sub px. Our goal for this step is to show that every a in the set 1 through p minus 1 is a root of h. Take any a with a's between 1 and p minus 1. Since a is non-zero in G sub p, Fermat's little theorem gives a to the p minus 1 is equal to 1 in G sub p. So HA is equal to a to the p minus 1 is equal to 1 minus 1 is equal to 0. That means a is a root of h. Since this works for every a from 1 to p minus 1, we have p minus 1 distinct roots, one for each non-zero element of G sub p. A quick sanity check. A is equal to 0 is not a root because h0 is equal to 0 minus 1 equal to -1, which is not equal to 0. So we have exactly p minus 1 root. A is equal to 1 through p minus 1. Now we turn those p minus 1 roots into a full factorization. 3 steps. Step 1. Because each a is a root of h, corollary 6.2.3 tells us x minus a divides hx. Step 2. The p minus 1 elements, 1 through p minus 1, are all distinct. So the linear factors x minus 1, x minus 2, up to x minus p minus 1 are pairwise co-prime irreducibles in G sub px. By the analog of the Chinese remainder theorem for polynomials, their product divides hx. So product of x minus a divides hx. Step 3, here is the key move. Both product of x minus a and hx are monic polynomials of the degree p minus 1. If a monic polynomial divides another monic polynomial of the same degree, they must be equal. There is no room for any additional factor. Therefore, x to the p minus 1 is equal to x minus 1 times x minus 2 times up to x minus p minus 1 over G sub p. Step 3 is the moment where p minus 1 root witnesses get promoted to a complete factorization. Without the degree argument, we would only know the product divides h, not that they are equal. Now substitute x is equal to 0 into the identity we just proved. Left-hand side, 0 to the p minus 1 is equal to negative 1. Right-hand side, product of 0 minus a, which is equal to negative 1 times, negative 2 times, up to negative p minus 1, which is equal to negative 1 to the p minus 1 times p minus 1 factorial. Equating the two sides, negative 1 to the p minus 1 times p minus 1 factorial is congruent negative 1 mod p. Now we handle two cases. P is an odd prime, p minus 1 is even, so negative 1 to the p minus 1 is equal to just 1. The equation reduced directly to p minus 1 factorial is congruent negative 1 mod p. P is equal to 2. 2 minus 1 factorial is equal to 1. And in G sub 2, we have 1 is equal to negative 1. So the congruence holds trivially. In both cases, Wilson's theorem is established. P minus 1 factorial is congruent negative 1 mod p for every prime p. Let's recap the argument in 3 bullets. Fermat gives p minus 1 distinct roots of x to the p minus 1 minus 1. Factorization plus degree match turns those roots into equality. Substitute x is 0 to extract the factorial and get Wilson. Now let's verify everything for p is equal to 5. hx is equal to x to the 4th minus 1 in G sub 5x. Root check. 1 to the 4th is equal to 1, 2 to the 4th is equal to 16, which is congruent to 1. 3 to the 4th is equal to 81, which is congruent to 1. 4 to the 4th is equal to 256, which is congruent to 1. So all 4 are roots as expected. Factorization, x to the 4th minus 1 is equal to x minus 1 times, x minus 2 times, x minus 3 times, x minus 4 over G sub 5. Plug in x is equal to 0, left-hand side, negative 1, right-hand side, minus 1 times, minus 2 times, minus 3 times, minus 4, which is equal to negative 1 to the 4 times 4 factorial, which is equal to 24, which is congruent to 4, which is congruent to negative 1 mod 5. Wilson, 4 factorial is equal to 24, which is congruent to negative 1 mod 5. You can try p equals 7 on your own. Compute 6 factorial is equal to 720 and check that 720 is congruent to -1 mod 7. Three things to take away from this problem. 1. Polynomial root counting combined with a degree argument is a powerful mechanism. It converts Fermat's little theorem, a statement about individual element, into a global factorization identity. 2. The logical chain is clean. Fermat, root, factorization, constant term comparison, Wilson. Each step uses exactly one tool from our list. 3. Wilson's theorem also runs in reverse. If n-1 factorial is not congruent to -1 mod n, then n is not prime. This makes Wilson's theorem a primarily criterion, though not a practical one for large n. That wraps up this problem. Thanks for watching. We'll see you in the next one.